So our next speaker is Bracken Dawson. I'll let Bracken introduce himself and going to talk about Delta printers.
Hi everyone, so I'm Bracken Dawson. By day I work for IBM. I make IBM's cloud. But more interestingly, by night I like to play with 3D printers. And it was 3D printers that got me into this community somewhat. Because I don't know if anyone remembers seeing the article on Hackaday about the $300 3D printer, which was the original RepRap, I believe, got posted there. I saw that at university and thought, I'm definitely going to make one of those for myself. Don't ask my password. It took me until 2012, once I'd left university and graduated, to actually make one. I put together a Prusa Mendel in 2012, which seems to be the year everyone else got into it. And then at the end of that, thought, I've got a 3D printer. I'm not a member of a makerspace. I know what makerspaces are. So I went out into Southampton to try and find my local one, discovered there wasn't one. So me and 5 other of my friends started the Southampton makerspace, which is still running today, and I think probably still has a focus on 3D printers quite a lot. So now you know a little bit about me, I'd like to sort of gauge the audience a bit. See a show of hands for who here would say they're familiar with 3D printers. Maybe you own one, maybe you use one at a school or a makerspace. It's about 50%, that's pretty good. And who here would say they're familiar with Delta printers? Ooh, largely the same group, but not everyone, that's good. So, Delta printers, and we've got a little video I can go here. This is, ooh, noise, we don't need that. No, we don't have mute. So this is the video of the original Rostock, which I think captivated many people when they saw it first on YouTube. It's probably shared on Hackaday as well. It's a different way of moving 3D printers around. As you can see, there's a carriage here, which is known as the effector, and that's moving in very parallel manners. And it's actually driven by these 3 carriages on the vertical pillars. So the motors drive the carriages, and through the arms it drives the effector around, and it stays perfectly flat. Make that quiet. So that's a Delta printer. Now, where did the Delta mechanism come from? So in about the early 1980s, Delta mechanisms were developed to make pick-and-place machines and then patented in 1990. So roughly at the same time that Stratasys were making their 3D printers, the Delta mechanism already existed. The two had not yet combined. In 2006, 3D printers kind of come to the hobby community, so we get the RepRap. And then in 2012, which is when I started making my Cartesian 3D printer, which is the regular flavor, the non-Delta ones, that's when the Rostock originally combined the ideas and put Delta machines together with 3D printers. So on the left, they've got pick-and-place machines. That's a much more recent one, and the Rostock on the right. So why would we make a Delta machine? The first reason is the reason I use for making Delta machines. And I think the reason most people use for making Delta machines is they're really cool. I mean, you saw the video, right? Another reason is they're fast. Because the carriages and the effector are very, very light, they can accelerate very fast. And acceleration in 3D printers is more important than top speed. If you've got a very high top speed that you can move at but a low acceleration, when you're printing a part this big, you're not going to reach your top speed running across here. So a fast accelerating machine is much more beneficial than a fast machine. Another advantage, they're quite tall, so usually about 1 meter tall. Mine is about this big. They suit scaling up quite well. Some other printers do as well, but the Delta machines do suit going up quite well. If you scale a 3D printer out in X or Y, the lateral dimensions, you often start to get problems with parts warping up. But scaling in Z is, it has very few limitations. The problem is you start to knock prints over as they get taller. But Z is a good dimension to scale a 3D printed part in. So I mentioned that the carriages are driven. There's a couple of options for this. The smart choice is this one, which is use a toothed belt. It doesn't require calibration, because the distance between the teeth on the belt is known. If you turn a 12-tooth pulley through 360 degrees, you've moved 12 teeth times the pitch of the belt. You don't need to calibrate it. It's really reliable, and it, again, scales relatively infinitely in Z. Eventually, they just get to be too much belt and there's too much stretch, but you can go quite a long way. The more cool way is the one I've chosen to use. So this is some pulleys, you can't really see it, with a thread cut into them. And that's Spectra line, which is the fishing line for catching sharks, which is really cool. The problem with those is you do need to calibrate it. So in theory, you should be able to work out the diameter of the part of the pulley that the thread sits in, but it's not that accurate, so you have to do a test where you move the carriage and then calibrate the number of stepper motor, that's these things, steps per millimeter, you have to do to get those to move the desired amount. The other trouble is they wear out, snap, stretch. Really, you should just go for a belt, but the fishing line for catching sharks is really cool. As I mentioned, tall. Another advantage of tall I found was that it takes a really long time to print tall things. So this is at the Bracken Mini Maker Fair. So my makerspace took along our Delta printer, which Mark Hindus and I built. And we left it for 6 hours printing a really tall TP model. And we printed this one in the spiral vase mode. I don't know if anyone has used that mode before. It's just, we print one perimeter in a spiral gradually going up. So it's a bit like a helter-skelter, and it just keeps going round and around and around and around in one continuous path. That really kind of shows off the deltas really nice, because the arms are all going up and down into their extremes. So it just looks quite good for a solid 6 hours without you having to touch it. Why not? There's a lot of reasons why not. Calibration. We'll get onto calibration in a bit, but they do need careful calibration or they won't work. Cartesian to delta. So this is done on the fly on most printers. So in a Cartesian printer, if we want to move 10 millimeters to the right in X, along like this, all it has to do is take the X motor, unwind it along a bit. In a delta machine, if you want to move 10 millimeters along in X, you've got to move 3 different motors non-linearly, and one of them is going to move and then move back again. It's going to reverse direction. So what the printers actually do is they cut that one move, which would normally be one instruction for a Cartesian machine, into lots of smaller segments and work out how to move each motor for those segments. And on the Arduino Mega, which is roughly the electronics I print with, this actually is a bit of a limitation. It would be desirable for that sort of a move to use 200 segments. But the floating point maths required to work out what each of those segments should be is a bit much for 16 megahertz on 8-bit architecture. So there's a lot of newer boards now where 32-bit running at 200 megahertz or higher, they can handle it. So I have to limit it to sort of 160 or so is the highest I've managed to get. The speed of the printers is a problem there as well, because they're moving so fast, they've got much more calculations to do ahead of time. But at 160, you start to actually hear that it sounds not very smooth, and you can start to see artifacts on the surfaces of the parts you make. So Delta printers really are pushing the limits of Arduino, and not just in processing power, because you'll find that they also use the analog to digital converter for reading temperature sensors. They use the PWM hardware for driving motors. They use pretty much all the peripherals and all the processing power of that poor Arduino. It really is the machine that pushes them more than any other I've seen, because a lot of them won't use most of the peripherals or won't use a lot of the I/O. The 3D printers just seem to use it all. Another downside, you typically, because of that light effector, have to use a Bowden extruder. Might change with some lighter DC motors operating in a servo style. I've seen a lot of people do that on a Delta recently, but nothing seems to have picked up in popularity as a one design that everyone uses, much like the Wade's extruder did. And the Bowden extruders, they're a bit like Bowden cables on a bike, except pushing rather than pulling. So we push the filament through a tube from a motor far away down to the extruder to keep the heavy motor off the extruder. But the springy nature of that Bowden setup creates a bit of a delay in what happens at the extruder. So they're a bit harder to get working. Not much these days. That's another downside, perhaps, of the 3D printers. And the calibration, there's 2 really important dimensions on a Delta machine. So this is, again, kind of looking at the front. We've got one of the pillars here, the carriage here, the rod and the effector. The 2 important ones is how long the rods are and the distance from where the rod meets the effector to where the rod meets the carriage, that way. This one is really easy to get right, because you can put your rods in a jig when you make them. This one is quite difficult to get right, because you typically aren't able to tweak it when you're making a printer, and it basically depends on how well you printed the parts the machine's made out of, or how well you assembled the frame. And if you get either of these wrong, the impact is that when you ask the printer to do a straight line or move around in a plane, it'll actually move in a concave or a convex manner instead. So what we have to do is the printer will move around the bed and sense where the bed is. And it thinks it's moving flat, and it senses the bed. And then you'll end up with a point cloud, and that point cloud will look to the printer as being convex or concave, even though your bed is perfectly flat and you know it. And this is because of the inaccuracy in one of those measurements. And the firmwares, having taken this point cloud, will tweak one of those measurements until the point cloud they've seen would be flat. And once they've seen that, then they can use this as a means through which to print. So they can correct for any inaccuracies. They'll just change what they believe this dimension to be in their firmware. So they're essentially measuring themselves. They also find out where the bed is. So it's quite critical on your first layer to get the first layer height right. And a few, even fractions of a millimeter off can make quite a big difference. So that's useful for finding exactly how high the bed is as well. Another interesting part is the rod ends. That's the part that connects the rod and the effector and the rod and the carriages. I tend to use the things on the left, which are rod ends from the suspension parts in remote control cars. They're really cheap because China makes them by the million. They do have a little bit of play in them, which is sort of a bad thing. You find that some of the printers, when they do that calibration, will actually do it in a series of steps until they actually do a run which comes out flat enough with intolerances. And if you have a lot of play in those joints, this step will just repeat and repeat and repeat it, and it will never be able to find something that it thinks is a good enough calibration. But those tend to be good enough, depending on the quality you get. The next one here is from a G-Tech Delta printer. They're using essentially the same part, but from a car, which has those ones are quite reasonable quality. They've got very little play in them at all. Or rather, they would have very little play if they'd made this collar right, because they put a lot of play in there. So this was a machine brought to the makerspace that, again, wouldn't finish calibrating. Once we ground down those collars to be the right size and got all of the play out, that one did finish calibration. But the problem with that one is, because those are so heavy, when the machine had finished calibrating, it would move the carriage to an idle position while the heater heats up. And after 30 seconds of not moving, the motors turn off on these printers. Normally, the resistance in the motors leaves the machine where it is. But because the carriages and the effector and the rods were so heavy on this machine, after 30 seconds, the thing would just plummet and drive the nozzle into the bed, and of course lose all calibration. So I wouldn't recommend getting the G-Tech Delta if you buy a Delta kit. Probably the most advanced right now is this method, where someone's glued some spherical magnets onto the end of their carbon rods, and they've got I think it's at the head of a bolt, and it just sits in it. And this moves smoothly, and there's absolutely zero play in it. So that's probably the best method that exists today. I mentioned that the thing touches the bed to find where the bed is. It doesn't necessarily touch it. There's quite a few methods I've seen of finding the bed. My favourite, and on my printer on the left there, that little red box sitting next to the metallic arrangement which extrudes the molten plastic is an inductive proximity sensor. That one works with metal beds, and it will tell me when I'm about 10 millimeters above the bed. The problem here is there is an offset, both in it's not under the nozzle, so I have to tell the firmware, actually my sensor's over here, and when I've finished calibrating, the nozzle's going to be a few millimeters above the bed. So I need to say, oh, and also it's 3 millimeters lower than you think-ish, and that depends on what material I've got on the bed as well. So if I put the blue tape that PLA prints quite well onto on the bed, that will change how soon that detector finds it. There's also capacitive sensors. They work on many more materials more reliably. Going back to the G-Tech, which you shouldn't buy, they've actually got an Allen key type thing here, And the idea is you, with your finger, lift it up, turn it round, and let the spring push it against this micro switch. So whenever the nozzle, the effector comes close to the bed, it pushes up that Allen key and releases the micro switch. And then when it's finished calibrating, and before it's about to plummet into the nozzle again, their idea was you would reach back in with your hands and clip it out the way. I've seen some versions of that where they actually use one of the pillars up the side of the printer to unhook and hook the probe, so it moves in just the right way to push it down and then to seat it back up again. That's quite neat, but it's a bit complicated. Again, it has an offset to the bed, so you have to account for that, and it's an offset from the nozzle. My favourite one is probably methods where you have sensors underneath the bed. So in this case, we've got a glass bed. It doesn't have to be metal, and at various points there's these little pads here. This is a fairly new component that's been available for about 4 years now, called a force sensing resistor. So the idea is we actually use the nozzle itself to touch the bed. So you'll see the printer, when this one does the calibration, it'll come along and do this grid on the bed, and the nozzle will just gently kiss the glass, and it will sense it and move away again. The advantage of this one is there's no offsets whatsoever, because it's the actual nozzle touching the bed. So when you've finished calibrating, 0, 0, 0 in coordinates will be the exact middle of the bed, touching it, only just. So that one's probably the best one to go for right now. Although Adrian just told me of another method that's similar, using springs to push the bed down lightly and complete an electrical connection. I think that one could possibly be more reliable, because you can fool this one by, if one of these screws is a bit tight, or you just lean on the bed, it'll think the nozzle's touching it. Does anyone know what G-code is? I think most of the people with printers will. So this is a command sent to a printer, which is to tell it where it is. You might be lying to it, you might be telling the truth. So in this case, in a Cartesian printer, you could move it to the middle of its bed and then say, actually, you're on the corner of the bed. And a Cartesian machine, so long as you stay away from the limits, will continue to print pretty okay there. You'll just end up somewhere else on the bed. If you try this command in Marlin firmware on a Delta machine, you end up with the problem that on a Cartesian machine, if you want to move to the right and you're over here, and you want to move to the right and you're over here, that requires exactly the same movement of exactly the same motor. So moving the X motor will wind you along. If you're here, if you're over here, if you're up there, it'll just produce the same movement. The same movement of the same motors on a Delta, if you're over here versus over here, produces extraordinarily different results, usually going down and up, and in the case of trying to use this command, moving the carriages away from each other longer than the rods and the effector, so it rips itself apart, which is fine if it's one of those magnetic ones, because you can just bring it back together and clip everything in again. If you're using rod ends, you usually snap filament and stuff like that. So that command isn't safe to use on Marlin on Deltas. I don't know about other firmwares. I haven't tried, except for Z. You can move up and down in Z and it makes no difference on the Deltas. But X and Y, you should never lie to the printer about where it is. It was a bit spooky when we first tried that one. I was in the makerspace late one night with Mark, and we only moved it a little bit, but the next time we gave it an instruction to move, it did the thing where the carriages just both go in opposite directions and it tries to rip itself to pieces. So finally, these are some of the boards we use. So on the left is I've forgotten its name, the ramps board. I suppose a few of you are familiar with the ramps board. You can use that for a Delta. You just have to remember that where it says X, Y, and Z on these stepper drivers, it's actually now A, B, and C. And the same thing happens throughout the firmware when you're programming the board. As I said, it's pushing the limit running a Delta off a 8-bit Arduino. So a better option, which I haven't gone for yet, is to pick up one of the new 32-bit boards. So that's a smoothie board there. They produce, as the name implies, much smoother movement. So you don't end up with the machine occasionally just stopping as it's buffering new instructions for where it's going to move to. You can use finer grain delta segments, which is the name for what it breaks your movements into. And then that produces much smoother finishes on your prints. So that's all I've got slides for. Has anyone got any questions on Delta printers?
So you mentioned a few ways that a Delta printer can quite effectively rip itself apart, and I know there are a few others that you haven't mentioned as well, but it's all part of the same thing. I haven't been paying attention for the last few years, but are you aware of any techniques that anybody's come up with for the printer noticing that it's about to tear itself apart and stopping?
So I've heard suggestions, although I've never seen it implemented, of using servo drive rather than stepper motors. I think that's been suggested on the Cartesian machines as well, for making sure they're in the right position, because the Delta machines, like the Cartesians, are an open loop device. They don't, from the point of calibration to the end of the print, they don't know where they are. They just trust that every single one of those billions of micro steps to the stepper motors happened flawlessly. And servos would probably solve that. Otherwise, I haven't seen anyone try to stop them ripping themselves apart. Generally, it doesn't happen that often. It only happens when you're doing something new. Once you've got a machine printing, a Delta machine printing, it will just print for you. And in fact, sometimes more reliable than a Cartesian machine because of that calibration step at the start. In fact, I moved I put a bed probe on my Cartesian machine now as well, because when I started printing with a Delta, the fact that the min Z probe not being a ZN stop not being there was just so much better than having to tweak the ZN stop to get my first layer right, because it just did it right every time. Yes?
For the math, can you use fixed point arithmetic on a 8-bit machine, or do you need a soft load implementation?
So Marlin is using floating point. You can use fixed point. And the easy answer really is to get one of those 32-bit boards and do floating point, I think.
Single precision is enough?
Yes, single precision is enough. Sorry, what was that?
Can you get away with 16-bit
16-bit
floats?
floats.
Or is that too precise?
I don't know whether you can. I would expect you could, because 32-bit is good for a computer game at 1-to-1 scale with the real world, right the way out to about Mars, in terms of sort of millimeter accuracy. Any Kerbal Space Program player will know from the old 32-bit days, once you get out to about Pluto, then meters start to become a little bit fuzzy. But, but yeah, 16 should be enough.
Thank you very much, Bracken.
Yep.
I imagine Bracken will be around afterwards.